Hey, everybody. Today we're going to learn about two new concepts. Well, one new concept, but two simulations of the new concept, and something that's related to it. And the concept is the Doppler effect, and a related concept is a sonic boom. Now, you are all familiar, I think, with the Doppler effect. You've probably heard it, and you are certainly aware of the application of the Doppler effect when it comes to predicting the weather. Have you ever heard of Doppler weather radar? They're using the Doppler effect to make predictions about how storms are moving, how fast they're moving, which direction they're moving. And you can certainly do your own research to find out more about that. I'm going to talk about some basics about what the Doppler effect is, how it affects the sound we hear. Of course, Doppler weather radar is not with sound, it's with electromagnetic waves, radar waves. But we're going to talk about how it works with sound. You're not going to do any of the equations. You just need to know how the frequency of a sound wave is affected by the Doppler effect. And in order to see this happen first, what you need to know is if you've done the reading, if you haven't read section 6 of chapter 14, you should do that first. But if you've done the reading, you know that the Doppler effect occurs whenever there is relative motion between a source of sound, you can see here source velocity, and an observer of the sound, or a listener, if you will. All right, whenever there's relative motion between source and observer, you get the Doppler effect. All right, now what does it look like? Well, first of all, I'm going to show you what it looks like when there is no relative motion. So in other words, when both the, this is being very picky. Okay, there we go. When both the source and the observer are not moving, okay, and I'm going to hit start, and you'll see the source is emitting sound waves, and the sound waves are going out in all directions. And you'll notice the distance between the waves. These waves, they're sound waves, so they're longitudinal, but you can think of these as crests. You'll notice they're all the same distance apart. Okay, so I'm going to hit reset. That's what happens when there is no relative motion. Now, what if the source is moving towards the observer? And we'll say with some reasonable speed, maybe about 10% of the speed of sound. Okay. All right. So what happens when the source is moving toward the observer at 10% of the speed of the sound? What you can start to see, all right, and I'll pause it. What you can start to see is that the sound waves, the crests in front of the source, right? The source is moving towards the observer here. The crests in front of the source get closer together, and behind the source, they get farther apart. Now, if you're saying, well, Mr. Morgan, that's really subtle and not really easy to see, you're right. Okay. But watch what happens as the source velocity increases. I'm going to put it up here around 20% of the speed of the sound waves. Okay, so the sound waves are 343 meters per second, 20% of that, and you can really start to see a difference. Okay, now I'm going to move it up to about 70%, around there. Okay, let's see here, somewhere in this range. Okay, now watch what happens. When the source is moving that fast, you'll notice that the sound waves in front are really piling up on each other. The waves are very close together. Or, in other words, the wavelengths are shorter, right? The distance between these crests is smaller. And over here, behind the source, the distance between the crests is longer. So, as the source is moving towards an observer, what you hear as the observer is the shorter wavelengths, which of course means higher frequencies. You see, perceived frequency is way up. The actual source frequency is 343 hertz, way up high, the perceived frequency. Okay, why? Because the waves are getting squished together. You like that scientific term, squished? The waves are getting squished together out in front of the source and elongated behind the source. So what you hear is a higher frequency. Okay, and that's the Doppler effect. The shift in frequencies between a moving source and an observer, or when there's relative motion, and it changes, right? In front of the observer, sorry, in front of the source, the waves get closer together. Behind the source, they get farther apart. Okay, if I keep this going, you can see that. All right, now notice when the source passes the observer, now the observer is hearing these elongated waves, and longer wavelengths mean lower frequencies. Did you see that right here? 207. So now that the source has passed the observer is no longer hearing a higher frequency as they did when the source was approaching the observer. The observer is hearing a lower frequency because the source has already gone past. We'll do it again. All right, now I'm going to do this once for you. I am going to one time give you some semblance of a demonstration of what it will sound like, right? And I am not trying to match frequencies. I'm just giving you some idea. As the source approaches the observer and then moves past the observer, listen to the sound I'm making and listen to how the frequency of the sound changes when the source moves past the observer. All right, I hope this works. I'm not sure how good this mic is going to pick up what I'm saying and doing and the bandwidth and all that, but we're going to give it a try here. Okay. All right, so let's reset. Now remember, as it approaches the observer, the waves are squished, so the frequency is higher. And after it passes the observer, the waves are elongated, so the frequency is lower. Are you ready? That was pretty good. I didn't say so myself. But anyway, that's the drop in frequency. Really high pitch, lower pitch. Okay, so that's the Doppler effect with sound waves. Now, this is a simulation that you can do. The link to this simulation website is on. There's a link in your Schoology folder under Waves. There's another one under Waves here, and I'm going to show you. This one says the Doppler effect and sonic boom. The other one also says the Doppler effect and sonic boom, but you can find it in a different place. If you go to Waves tutorial and then go over here and go down to the bottom, but you can find them all. But this also shows you the difference between what the observer in front of the source hears, higher frequency, and the observer behind the source hears, according to the Doppler effect. Okay. Now, there's one last thing that this also shows you, and it talks about the sonic boom. And this happens when the source is moving so fast that it's moving almost as fast as the sound it's making. The speed of sound in air is 343 meters per second. As you approach and then exceed 343 meters per second, the waves start to pile up. And where those waves pile up, you get what is called a sonic boom. And you can see it even more dramatically here, where the source is moving so much faster. Let me see if I can pause this. Is there a pause somewhere? I don't see a pause button. Let me see if I can just make it pause by clicking. Nope. But you can see this triangle of waves building up. All right. And those waves, what they are is a pressure zone. All right. There's crushing pressure. And if you've ever seen an air show, for instance, where supersonic jets are flying, you've experienced this. The sonic boom, this buildup, this pressure zone of air as the waves are interfering with each other, create this sonic boom. But that's a very special effect of the Doppler effect that only happens when the source is moving faster than the waves it's producing. So, in other words, if you exceed the speed of sound in this particular case. All right. Okay, good. Please feel free to play with these, mess around with this. You can see this is another version of the one we just saw before, as much as you want. And be sure to do the reading and also the conceptual exercises that are in the update. All right, and there will be a quiz on Monday. Thanks, everybody.